How's everyone doing? Is today going to be a really long review session? I mean, it depends on if people keep having questions. So, yeah, actually, I need to change, as usual, I need to change the office hours. So I'm not having office hours right after um, lecture. We're just going to continue lecture for another hour or so um, to do review. And then I'll have office hours later today. Um, let's say at 6 o'clock. Let me change that real quick. Let me schedule that real quick. There we go. Okay. Yeah. So office hours at 6 later today, and yeah, we'll continue this for like another hour or so after class. Okay. So, what do we want to look at? How badly did I do on the solutions? Let's find out. So yeah, it turns out, I think, let me, yeah, so I think some of the questions have changed apparently, a couple of them. So number 13 was actually quite annoying. But yeah, it's not the hugest deal. Anyways, so what do we want to look at? What questions or what would you like me to talk about, etc. Number 12. Alrighty. All right, let's do number 12. And we can take a look at number 6 after. Okay. Okay. So we have a triangular city. Which has vertices at 0, 0, 0, 4, and 2, 0. And it has population density 1 plus 2x in thousands. Per square mile. So let's calculate, whoops. First, let's calculate the population. My goodness. Total population. Wow. Am I having a stroke right now? I can't spell population. Total population. All right. Okay. So total population is let's call our city region D. It's going to be the integral over D of, well, let's draw whatever. Let's draw our region first. So we have vertices at 0, 0, 0, 2, or 2, 0, and 0, 4. Okay. So our total population is, of course, the integral over D of the density, the population density, with respect to area. So let's find the bounds and plug this in. Okay, so we're integrating over triangle. What makes the most sense? So we could either do polar or we could do top and bottom curve, left and right curve. How do we want to do this? Right, so it makes sense to do rectangular. There are no circles involved here. In fact, you could do top and bottom curve, or you could do left and right curve. It's vertically and horizontally simple. I prefer to do top and bottom curve when I have the option. So let's bound y by functions of x. So our bottom curve is, of course, y equals 0. And our top curve is y equals 4 minus 2x. So y is bounded by functions of x. So we're going to integrate with respect to y first. So y goes from 0 to 4 minus 2x. And x goes from what to what? From 0 to 2, right? Okay, so let's do our integral here, integrating with respect to y. So everything but y is a constant, so 1 plus 2x is just a constant. That becomes 1 plus 2x times y. And we're evaluating that from y equals 0 to 4 minus 2x. How'd I get the 1 plus 2x part? Because we're given that as the density. So we're integrating the density over this region, the population density. It happens. And so this is 4 minus 2x times 1 plus 2x. And when we FOIL that out, we get 4. So minus 2x plus 8x, so that's plus 6x minus 4x squared. And so we plug that into our inner integral. Did I already, hang on, let me add my solutions here. Did I screw that one up? We'll see. We'll see. Okay, so we get, so the integral from 0 to 2, x goes from 0 to 2 of 4 plus 6x minus 4x squared dx. And so we get 4x plus 3x squared minus 4/3 x cubed from x equals 0 to 2. So we get 8 plus 12 why does it do that? Minus 32 over 3. So 4 times 8 over 3. So we get 60 over 3 minus 32 over 3. We get 28 over 3, which is not what I got, I believe. Yeah. So So I got 8 over 3 there. I think I accidentally put this as 1x squared, and then that would explain the answer I got. But yes, it should be 28 over 3. Thousand. Okay. So let me make note of that. Mistake number 1. This is number 12. A, we get 28 over 3. And B. So the population center. Which functions like the center of mass, essentially. So we find it the same way we find the center of mass. The x-coordinate of the population center is going to be 1 over the population times the integral, over the city of x times the density and so plugging that in, we can use the same bounds for our integral. X goes from 0 to 2, y goes from 0 to 4 minus 2x. Sorry, 1 over the population's 3 over 28. And so that's x times 1 plus 2x, which is x plus 2x squared. dy dx. And so I didn't show the integral for this, but get in the habit every time you're doing a double integral or triple integral, seeing if you can simplify before you evaluate the integral. So the first thing you should do when you look at a region, an integral, and you have sketched the region of integration, is think to yourself, is there any symmetry in this region of integration? So there is none here, but it's a good thing to get in the habit of checking every single time. So check symmetry about x equals 0 in the x direction, symmetry about y equals 0. And if you have either of those, then either x odd or y odd terms, depending on the symmetry, integrate to 0. But we have neither here, so can't use symmetry in this one. Okay. So the inner guy we get is 1/2 x squared plus 2/3 x cubed. Rather annoying. Whoop. Sorry. Nope. Not yet. All right. My bad. Okay. Integrating with respect to y. So we get y times x plus 2x squared from y equals 0 to 4 minus 2x. And so we get 4 minus 2x times x plus 2x squared. So we get the same thing as we got over here, except multiplied by x, essentially. So we get 4x plus 6x squared minus 4x cubed. And so then we plug that into our outer integral. And don't forget the 1 over the population, 3 over 28. Integral from 0 to 2 of 4x plus 6x squared minus 4x cubed. So 4x, we get 2x squared. 6x cubed, we get 2x cubed. And minus 4x cubed, we get minus x to the 4 from 0 to 2. And so we get 3 over 28. So 2 times 4 is 8, plus 2 times 8 is 16. Minus 16. And so we get 3 times 8 over 28. So we can divide top and bottom by 4. And so we get 6 over 7. For our x coordinate. And then really quickly, let me do the y coordinate. So the y coordinate is, of course, 1 over the population times, I'll just write it out. So 1 over the population and the integral over the region of y times the density, which is 1 plus 2x. And so we get inner guy 1/2 y squared times 1 plus 2x, evaluated from y equals 0 to 4 minus 2x. Okay. So 4 minus 2x squared, we get 16 minus 16x plus 4x squared times 1 plus 2x. I'm just going to distribute that 1/2 through to make life a little easier. So, and then expand everything out. 8 minus 8x plus 2x squared times 1 plus 2x. And so we get 8 minus 8x plus 16, so plus 8x, minus 16x squared plus 2x squared, so minus 14x squared, and then plus 4x cubed. And integrate that from 0 to 2. Make sure. 8. Wait. Yep. Yes. Yes. 8 plus 8x minus 14x squared. Right. So that's 16 minus 16 plus 2. Yes. And don't forget the 3 over 28. So we get 3 over 28 times 8x plus 4x squared minus 14 over 3x cubed plus x to the 4 from 0 to 2. And so we get 16 plus 16 minus 14 times 8, which is 112. Over 3, and then plus 16. And so we get 48. So 48 is 144 over 3. So 144 minus 112 is 32. And so we get 8 over 7. Okay, so the population center is 6 over 7, 8 over 7. Should be. Is that what you got, Ryan? Okay, yes. Sorry about that. First of several mea culpas, I'm sure. Okay, and then we want to look at number 6. Okay. Number 6. Okay, which ones did you want to look at in particular? Thomas. 6A? All right. So part A, we want to calculate these in whichever coordinate system is most appropriate. So integral over the region E of xz with respect to volume. E is going to be the region. Inside the sphere, x squared plus y squared plus z squared equals 4 in the first octant. Okay. Not great at drawing a picture, but I think everyone can imagine the quarter of this sphere. Sorry, the eighth of this sphere, which lies in the first octant. So you take the top half and then you look at the bit where X, Y, and Z are all positive. Okay. So it's inside a sphere. It's a piece of a sphere. So clearly the most reasonable coordinate system to use here would be spherical. So whatever, let me sketch, do my best here. So pretend that's our quarter sphere, or our eighth of a sphere here, the bit of the sphere in the first octant. Okay. So we need to find our bounds for rho, phi, and theta. Okay, so what are our bounds for rho? So 0 to 2, right? So we have the origin in there, and we go out to the outer boundary is the sphere, which is rho equals 2, right? X squared plus y squared plus z squared equals 4. It's a set of all points of distance 2 square root 4 away from the origin. So rho goes from 0 to 2. Phi goes from what to what? So we have the positive z-axis. That's phi equals 0. And then we go down until we hit the xy plane. That's the largest angle we make with the positive z-axis. That goes from 0, and then the xy plane is pi over 2. Phi equals pi over 2. And then how about theta? So we're going around the z-axis, starting on the positive x-axis. So we have points on the positive x-axis. That's like the furthest clockwise, in the clockwise direction. And then we go counterclockwise. So that's theta equals 0. We go counterclockwise until we hit the positive y-axis, which is theta equals pi over 2. Okay, so let's set up our integral. We have the integral. Theta goes from 0 to pi over 2. Phi goes from 0 to pi over 2. And rho goes from 0 to 2. And then xz, x is going to be rho sine phi cos theta. So remember, in cylindrical, x is r cos theta. And just remember r is rho sine phi. In spherical. So cos theta. Z is rho cos phi. And then dv in spherical is rho squared sine phi. Okay, gonna do that. Rho squared sine phi, d rho d phi d theta. And so we get integral 0 to pi over 2, 0 to pi over 2 for phi, 0 to 2 for rho. Okay, so we have rho squared, so rho to the 4. Sine phi times sine phi, so sine squared phi. Cos phi. And then cos theta. Okay. So far, so good. This was the integral you had set up? Okay, so integrating with respect to rho, rho to the 4 becomes 1/5 rho to the 5. Ah, you see? Okay. I'll skip some steps here. Let me make sure I did everything correct here. Yeah, so we got 32 over 5. Right. Sine cubed. Right. Yep, okay, yeah. So we should get 32 over 15 in the end. Don't want to spend ages evaluating that. But yeah. So 6A was the only one you wanted to look at for number 6? Gonna get some water super quickly. So figure out what problem you want to look at next, and we'll check that out. (13A), okay. Okay, so you know what? The reviewer changed this problem, so let me to make it quite a bit simpler. I might post that, and then we'll just do the problem here. I'll post the updated one. And he also has solutions, or not solutions, just the answers.
Wait, sorry. So what was changed about 13?
The only thing that was changed was instead of the region above z equals 1, it's now the region above z equals 0, which makes all the bounds a lot nicer to deal with. But let's take a look at it. So I'll work out the problem with the new one, and I will post the updated one, because yeah, it wasn't that, it was kind of nasty to deal with, honestly. It wasn't too bad, but it would take a while in the context of an exam. So let's look at that. Yes, I'll post the answer key as well. This we got last night. So okay, so 13. So same thing. So our region is inside the sphere, x squared plus y squared plus c squared equals 4. But now we're looking at the region above z equals 0 instead of z equals 1. Whoops, not now. I'm literally writing down what I'm saying. And above z equals 0. Contains charged particles. And it has charge density. Sorry, not rho, let's say delta. bad habit. Or actually they use gamma, never mind. So charge density, X plus Y plus Z. So let's find the total charge. In this region. Okay. So the total charge, of course, well, let's sketch our region. So we have the sphere centered at the origin of radius 4, and we're looking at the top half, the region above z equals 1. Before it was above z, z equals 0. Before it was above z equals 1, which made things a little more annoying. But now it's nice and simple. So that's the top half of our beautiful sphere. Okay, so remember, get in the habit really quickly of checking symmetries. It's going to help a lot in this problem. So our region is symmetrical. There are 3 possible symmetries for a 3-dimensional region. Are we symmetrical about x equals 0? Symmetrical in the x direction, right? X equals 0 is the YZ plane. Do we have a mirror image in front and back of the YZ plane? We do, indeed. So that means any x-odd terms are going to integrate to 0. Similarly, we have symmetry about y equals 0 in the y direction to the left and right of the xz plane. So that means y-odd terms are also going to integrate to 0. Do we have symmetry in the z direction? No, right? Nothing below z equals 0. So we can't say anything about z-odd terms. But x-odd terms, y-odd terms, those are going to integrate to 0. Okay, so the total charge, let me just say total. Let's call this region W, is going to be the integral over W of the charge density okay, yeah, first of all, well, hang on. Before we switch coordinate systems, let's use our symmetry, if possible, to simplify our integral. Before we find bounds and do any of that, because you're not going to be able to see the x-odd, y-odd, or z-odd terms after you switch coordinate systems. So do that before. So we're integrating x plus y plus z over this guy with respect to volume. So what are we left with when we kill off the x-odd and the y-odd terms? Right, so x is x-odd, that integrates to 0, that's gone. Y is y-odd, that integrates to 0, that's gone. Z is z-odd, but we can't say anything about just z-odd terms. So we're left with z. Okay, so let's find the bounds for this guy. What coordinate system do we want to use to integrate over W? Rectangular, spherical, cylindrical. Spherical. It's inside a sphere. It's in the name. Easy. Okay. So bounds for rho. So the origin's in there. So we're bounded below by 0. Remember, start your line at the origin, intersect it with your figure. Origin's in there, bounded below by rho equals 0. And the outer boundary we hit is the surface of the sphere. And that is, of course, rho equals 2. So rho goes from 0 to 2. Phi goes from what to what? So remember, I like to think of phi as starting at the positive z-axis at 0. If you have points on the positive z-axis, phi is bounded below by 0. And then opening up the cone until you hit the outer boundary of this guy. So we open it up until we hit the xy plane exactly. And the xy plane is phi equals pi over 2. And then remember, you keep going, if you can, until you hit phi equals pi, which is the negative z-axis. But at this point, we just open up until we hit the xy plane, and that's phi equals pi over 2. And theta, we're going all the way around. We get the entire half circle all the way around the z-axis. And so that's 0 to 2 pi. Okay. So our integral, when we switch to spherical, is going to be theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2. And theta goes from 0 to 2. And we're integrating z. So z, remember, in spherical is rho cos phi. And then dv becomes, remember, rho squared sine phi, d rho d phi d theta. So let's integrate that really quickly. Okay, so we get rho times rho is rho squared. Here, let me write this again. 0 to 2 pi. 0 to pi over 2. 0 to 2. Okay, so we get rho cubed. Sine phi cos phi. Or cos phi sine phi, doesn't matter. So doing our inner integral, integrating with respect to rho, rho cubed becomes 1/3 rho to the, or sorry, 1/4 rho to the 4. Sine phi cos phi hang around because they're constants. Rho equals 0 to 2. And so that's 1/4 times 16, which is 4. So 4 sine phi cos phi. So 0 to 2 pi. Phi goes from 0 to pi over 2. So 4 sine phi cos phi d phi d theta. So integrating that inner integral. So sine phi cos phi we can use sub. Let u be sine phi, and then du is cos phi d phi. So integral of 4u du becomes 2u squared, which is 2 sine squared phi from phi equals 0 to pi over 2. And so we get 2 times 1 squared. So we get 2. And then, yeah, this is a lot nicer to deal with than the previous one. Integral from 0 to 2 pi of 2d theta, which is, of course, just 4 pi. This is so much nicer to deal with.
Could we have split that integral up instead of doing it like one by one because they're all constants? Could we have used that theorem to split it up?
So you mean for like the theta?
Just like the whole thing. So could we have did this as three integrals in terms of rho, phi, and theta?
Yeah. You could have. You could have. You could have.
Okay.
It works the same way. Like you could take all the terms. So since it's just stuff involving rho and stuff involving phi, and then stuff involving theta, which is just constants. Yeah, you could if you like. So you
Okay.
could do like integral 0 to 2 pi, and then integral 0 to pi over 2, sine phi cos phi. Is this what you're talking about?
Yeah.
And then times integral 0 to 2, rho cubed d rho.
Yep. That's
Yeah,
it.
you could do that too. Yeah.
Thank you.
It functions exactly the same way, except you're just not carrying your constants around, basically. Okay, so we get the total charge, much nicer to deal with now, is 4 pi. All right, so part B, the solution or the answer key is actually wrong here because he did the center, a center of mass thing, which is kind of weird because it doesn't make sense. Like there's no like center of charge thing. And also doesn't make sense like physically, even if this was like mass instead, because mass is always positive and the density here can be negative in some spots, and it just doesn't make a lot of sense. But let's do the answer for the average charge density. So what is the average charge density on the region? Okay, so remember the average of a function in this case, the charge density. So the average of the charge density on our region W is going to be 1 over the volume of W times the integral over W of the charge density. So it's going to turn out there's not a lot of work to do here because we've already calculated the integral of the density over W in part A. So the integral over the density we already calculated, that is 4 pi from part A. And then we just need to find the volume of W. So the volume of W, you could calculate with an integral if you don't remember the equation for the volume of the sphere. And in fact, we needed to calculate this in the way that the problem was previously stated, because instead of being half a sphere, a hemisphere, the region above z equals 0, we got the region above z equals 1, which is, we don't have a nice formula for that. We need to actually calculate that one. But in this case, well, I'll remind you in case you forget how to do this. So the volume of W, so the volume of some three-dimensional region, of course, is just the integral over that region of the constant function 1. And so we would just, if we were doing that, we already found the bounds, we'd convert to spherical. So the bounds, theta goes from 0 to 2 pi, phi goes from 0 to pi over 2, and rho goes from 0 to 2. 1 is just a constant 1. And then dv is rho squared sine phi. D rho d phi d theta. And that's an easy calculation. So we get 4/3 times the radius squared, but we're only getting half of that, so it's 1/2 times that. It's 2/3 times the radius squared. So 2/3 times, the radius cubed. So 2/3 times 2 cubed is 16/3. Pi, yeah. So 16 pi/3 is going to be the volume when you calculate that out. Oh, sorry, that's not our answer. And so that's our volume. Oops. And so let's put this together. 1 over the volume is going to be 3/16 pi. And the integral of the charge density over W, we said was 4 pi. And so we get 3/4. Is the average charge density. Okay, so we get 4 pi for the first one, and then 3/4 for the second. Okay. And I will have to see what the other changes were, but I'll post the new one up. I'll do that like right now. What else do we want to look at? So number 8. Okay. Let's calculate the following integral. So the integral from 0 to 3, x goes from 0 to 3, y goes from 2x to 6, 4x over 1 plus y cubed. So dy dx. Okay, so almost always, if you get a problem given to you, like where the bounds and everything are already given to you, chances are, since that is usually the bulk of the points for these problems, finding the bounds and setting up the integral. If we've given you an already set up integral, chances are you're going to have to change the order of integration to evaluate. And that is indeed what we have to do here. So notice if we try to integrate with respect to y first, we have 4x, which is just a constant when you're integrating with respect to y. So it's a constant over 1 plus y cubed. And we're integrating with respect to y. So we don't know how to do that because we can't use sub or do any other kind of fancy sub in this. So what we're going to have to do is flip the order of integration. And then when we do that, we should be able to evaluate it. Otherwise, we wouldn't be giving you the problem. So we need to change the order of integration here. Okay. So in order to switch the order of integration, you can't just switch the bounds. Doesn't work. You need to sketch the region. And then in this case, first we integrate with respect to y. So first we treated it like a bottom curve and a top curve. Now we need to switch the order of integration and bound x by functions of y. In other words, we need to find the equation of a left curve and a right curve. X equals something, x equals something. Okay, so the bounds for y, so the bottom curve is y equals 2x. So that's, let's say that's y is equal to 2x here. And the top curve is y equals 6. And then x goes from x equals 0, which is the y-axis, up to x equals 3, which thankfully, that's this corner right here, because that's the point 3,6. It lies on y equals 2x. So that's our region of integration here. Okay, does everyone see that's our region of integration? Okay, so this is also, so this is a vertically simple region, top curve and bottom curve, but it's also horizontally simple, right? You do the horizontal line test, there's the same left curve every time a horizontal line intersects a region, and the same right curve. Okay, so we need to figure out the bounds for x. So our left curve is going to be this vertical line here. That is x equals what? X equals 0, right? And our right curve is the same as the bottom curve. So the right curve is going to be this slanted line, but we need to write that as x equals something. Before we had it as y equals 2x. So when we write it as x equals a function of y, we get x equals y over 2. So we see switching the order of integration. So now bounding x first by functions, x goes from on the left, where x is smaller, x equals 0, up to on the right, x equals y over 2. And then y is going to be bounded by numbers now. Y goes from 0 at the bottom up to 6. So let's set up our integral. Y goes from 0 to 6. X goes from 0 to y over 2. 4x over 1 plus y cubed. dx dy now. So our integral. So we have 4x over 1 plus y cubed. The 1 plus y cubed is a constant. When we integrate with respect to x, 4x becomes 2x squared. So 2x squared over 1 plus y cubed, evaluated from x equals 0 up to y over 2. And when we do that, so 2 times quantity y over 2 squared is going to be, and then when we plug in x equals 0, we get 0, so that doesn't show up. So 2 times quantity y over 2 squared is going to be y squared over 4, or sorry, y squared over 2. 2 times y over squared over 4. And all that is divided by 1 plus y cubed. And to make life a little easier, I just multiplied the top and bottom by 2 to get rid of the y squared over 2 part in the numerator. So we get y squared over 2 plus 2y cubed. Does everyone see where that came from? Okay, so then we plug that into the outer integral. And hopefully we can now evaluate it. So you get y squared over 2 plus 2y cubed with respect to y. So we want to u sub. So we're going to let u be 2 plus 2y cubed, meaning du is going to be 6y squared dy. Let me make sure, did I do this right? Hang on. Should have. 8. Yes, I did. Good. Okay. Okay. So we want 6y squared dy. We have y squared dy. So it's 1/6 du. So you get 1 over 6. So then integrating 1 over u du, you get natural log u. So 1/6 natural log of 2 plus 2y cubed, evaluated from y equals 0 up to 6. And when we do that, we get 1/6 natural log of 2 plus 2 times 6 cubed. So 6 cubed is 218. Or sorry, 216. Yes, 216 plus 2 is 218. And then minus natural log of 2 plus 0. And you can simplify if you want, but don't waste your time, honestly. Just leave it as is. And that's our solution. The bulk of the points, of course, are going to come from noting that you need to change the order of integration and then finding the correct bounds. Okay, what else would we like to look at? What was the problem where I couldn't find the bounds? I don't think that one was fixed. For B. C squared equals 0 above the xy plane. Nothing else we'd like to look at?
I just have a quick question.
Sure.
Would they give us a problem like 4b where it's not bounded? Like, would they? Because I was just confused. Like, if that came up on an exam, I probably would be thinking I was doing something wrong if it wasn't able to be bounded, because it didn't say like that was a possibility.
So that was not fixed on the updated one. So, oh, it was changed. Okay. Yes. Okay, so that was. Yep. Okay, so let's do the updated version of that, which actually you can do. Okay, that's good. Natural log 434. For 6 cubed plus 2. Should be 216 plus 2. Oh, 2. You're absolutely right. I forgot the 2. Thank you. Right. 2 plus 2y cubed. I totally forgot the 2. Yes. Yes, absolutely. So instead of 218, it should be 436. Nope, sorry, 434. Yep. Sorry, I forgot the 2 times the y cubed. Let me note that. Yep. Sorry about that. Thank you for pointing that out. All right. Okay, so let's do the updated 4b. So before, what we got was so it was y equals x squared plus z squared. So that's going to be an elliptic paraboloid opening up in the positive y direction. And it's bounded by y equals 0, which doesn't really help us in that case. And then above the z-axis. So what we do is we get like the top half of this elliptic paraboloid. Yeah, so that's our elliptic paraboloid, and we get like the top half of it. And it just sort of goes off to infinity. And we're not going to be able to integrate this guy, I believe, not even with a an improper integral. But we changed it, or it has been changed. So we want to integrate over the region, I guess we call it, whatever, call it D. Z over x squared plus y squared plus z squared with respect to volume. So now D is going to be bounded by y equals 4 minus x squared minus y squared. So before it was just y equals x squared plus y squared. Now it's 4 minus x squared minus y squared. Sorry, x squared minus z squared. Y equals 0. and above the XY plane. Okay. So this one we can actually do. So 4 equals x squared minus y squared is going to be an elliptic paraboloid also, but it's opening in the negative y direction, and the y-intercept is 4. So we're inside that. We're bounded by y equals 0, which is the xc plane. This is really hideous. I'm sorry. Hang on. This is not much better. And we're getting the top half of that, the part above the xy plane. So instead of actually trying to draw that, I'm just going to say the top half. Is what we're getting. Okay. So there are different ways to do this. But there's definitely an easiest way here. Okay, so what we could do is we could do rectangular, and we could do a top surface and bottom surface. So top is z equals something, bottom is z equals something. But let's see what we get when we do that. So if we do that, we get z is bounded below by z equals 0, easy enough, and bounded above by so if we get z by, the top is the top half of the elliptic paraboloid, y equals 4 minus x squared minus y squared. So we want to get z by itself. So we get z squared is 4 minus x squared minus y. Take the square root, plus or minus. The top half is going to be the plus part. So we get z is 4 minus x squared minus y, square root of that. I'm going to go ahead and guess we're not going to get nice stuff when we do that. So let's not use rectangular. What we're going to do is we're going to do cylindrical. And we didn't see a lot of examples of this, or we didn't see any examples of this, but we can do cylindrical where instead of doing z and then r and theta are like polar in the xy plane, we could do y. And then r and theta work like polar in the xc plane.
I have a question.
Yes.
If it's bound above by the XY plane, why are we looking at the top half instead of the bottom half?
No, it's bounded. Sorry, it's not bounded. So it's awkwardly written here. So it's bounded by the paraboloid y equals 0, and we're looking at the piece which is above the xy plane. So not bounded above by the xy plane, it's the region above the xy plane.
Okay.
Yeah, yeah. Okay. Okay, so what we're going to do is we're going to let y be y. And then, so basically we're going to integrate with respect to y. We're going to have a left surface and a right surface. And then we're going to project down to the XZ plane. And we're going to use polar there. So in that case, in the XZ plane, now x is going to be the horizontal variable like it was before, but z is going to be the vertical variable. So x, the horizontal variable, we're going to call, it's going to be r cos theta. And z, the vertical variable, is going to be r sine theta. Okay, so here's how this is going to work. So let's find the bounds for y. Let me use red here. Okay, so y, oops, bounded to the left where y is smaller by the XZ plane, that is y equals what? Y equals 0, right? And the right surface is going to be the y equals 4 minus x squared minus z squared. But in cylindrical, with x r and theta, we don't want to see x and z. Sorry, y r and theta. We don't want to see x and z. We need y to be a function of r and theta. So 4 is fine. What is x squared minus z squared? So minus x squared minus z squared. If x is r cos theta, z is r sine theta. It's just r squared. So 4 minus r squared. So y is going to lie between 0 and 4 minus r squared. And then let's project down to the XZ plane. So when we do that, remember, look at the widest region we get. Look at the shadow of that on the XZ plane. And so the widest region is going to be where the paraboloid hits y equals 0. And we're looking at the region above the XY plane, so where z is positive. So we're getting the top half here of this guy. Okay, so let's sketch that in the XZ plane and then find the bounds for r and theta. Okay, so let me make a note of that. So that's going to be this region here. So that's going to be the intersection of y equals 0 and y equals 4 minus x squared minus z squared. So the intersection of those is going to be the outer bound, but we want the part of that above the XZ plane. In other words, the plane z equals 0, so where z is positive. So the intersection of those two, set the two equal to each other. You get 0 equals 4 minus x squared minus z squared. So that is, oh man, x squared plus z squared equals 4 in the XZ plane. So that's just a circle centered at the origin of radius 2, but we want the top half of that where z is positive. Does everyone see that bit? Okay, so what are our bounds in polar for r and theta? Well, we do the same thing. Start your line at the origin. Find your inner boundary curve, your outer boundary curve. Well, the origin's in there, so r is bounded below by 0. What's the outer boundary curve? Well, it's the bit of the circle, x squared plus z squared equals 4. That's a set of points of distance 2 away from the origin. So that is r equals 2. So r goes from 0 to 2. And theta goes from what to what? Where now theta equals 0 is just the positive horizontal variable, which is still x in this case. So we go from what to what for theta? Zero to pi, exactly. Okay, so we have our bounds now. Let's, hang on, let me see if I can. Ooh. Okay, I know there's a way to drag that, but whatever, we're not gonna. Okay, we have our bounds. Let's set up our integral. So you have the integral over this region of z over square root x squared plus y squared plus z squared. So let's convert to cylindrical with y. So theta we said goes from 0 to pi. R goes from 0 to 2. Y goes from y equals 0 up to y equals 4 minus r squared. Okay, so z is going to be, we said z is r sine theta. It's the vertical guy. X squared plus y squared plus z squared. So y stays y. We have y squared. X squared plus z squared is now r squared. And then dv becomes r still dy dr d theta. So let's just multiply through by r. We get r squared. So this looks like this might be not very pretty, but let's check it. Okay, so we integrate with respect to y first. Was this supposed to be y above? I feel like it's supposed to be y on top. Hang on. Oh, you're not supposed to integrate? Oh, thank God. Whew, cool. Ah, okay, so, well, okay. Jesus Christ. Okay. All right. So, okay. Well, this explains a few things here. So let's ignore, sorry. Let's kind of ignore what I just said. So it explicitly says to set up in cylindrical coordinates. Reading would have helped here. Wowza. I don't think that's what they meant for us to do there. Hang on, let me look at these solutions and see if he still uses R theta and Z. Okay, yes, that is indeed. Never mind. Okay, yeah, no, this is good. This is what it's supposed to be. Yep. Okay, so yeah, you can do cylindrical, where, so remember we said cylindrical is good for things which are symmetrical about an axis. Usually we take that axis to be the z-axis. And so we look at like cylinders about the z-axis, or paraboloids opening up in the z direction. And we use R theta and Z. So it's basically Z, project down to the XY plane, and then use polar. But you can also do it about other axes. In this case, our region was symmetrical about the y-axis, or part of a region symmetrical about the y-axis. And we took, so we did Y, and then project down to the XZ plane, and then use polar there. And that's essentially what we did here. Any questions about that example? Okay, so I will, when I write up some addendum to the solutions, let me put an updated solution for 4B. Okay. Anything else we'd like to look at? Three B. Okay. All right. So 3B. So we want to set this up in rectangular. So the integral over Q of x squared plus y squared plus z squared. Respect to volume. And here Q is going to be bounded by z equals y squared, z equals 2x, and x equals 8. Okay, so my artistic ability is somewhat limited here, but I think I can make it work. Okay, so z equals y squared is a parabolic cylinder. So draw in the YZ plane, z equals y squared. That's that guy. And then translate it along that curve along the x-axis. So we're going to go, it's a cylinder along the x-axis here, but we're going from x equals 8. And then we're also bounded by the plane z equals 2x. Okay, so here's our cylinder. We're also going to have a plane. Oh, come on, dude. Also going to have a plane on top of that guy, z equals 2x. And that is going to hit the origin at 0. Sorry, that's going to go through the origin, right? So it's going to look something like this sort of here. Okay, so at x equals 8, oops, we have the bit, oh my goodness. We have the bit of our cylinder. Okay, this is really ugly here. Yeah, use your imagination here. So we have the bit of the parabolic cylinder between x equals 0 and x equals 8. And then on top, we have z equals 2x, that bit of the plane. So this is z equals y squared. Can everyone kind of see what's going on there? Okay, so, all right. So we want to set this up in rectangular. So what's going to be the easiest way to do this? We have 3 options for rectangular. Top and bottom surface, so bound z by functions of x and y. Left and right surface, bound y by functions of x and z. Or front and back surface, bound x by functions of y and z. Right, so top and bottom is going to be nice because we're already given the top and bottom surfaces. So let's say it's z simple. So what's our bottom surface? Z equals y squared is the bottom guy. And the top guy is z equals 2x. Okay, so then we're going to project this down to the xy plane. Right, so what we're going to do is we're going to look at the shadow of this guy on there. So we're going to find the outer curve enclosing the region in the xy plane. That's the projection when we smash this down on the xy plane. So the widest bit is going to happen basically at the intersection of z equals 2x and z equals y squared. So project the intersection is equals 2x is equals y squared to the xy plane. Essentially, we're going to forget about z. Okay, so we got 2x equals y squared. So that is going to be x is equal to 1/2 y squared. And x is going to go from 0 to 8, which we already know. So x is 1/2 y squared. X goes from 0 to 8. So that's going to be this guy. And let's see what happens with y there. Y is going to be going from +4 to -4. All right, when x is equal to 8, 1/2. 8 is equal to 1/2 y squared, y is ±4. Okay. So when we do that, we get a left and a right surface. X is bounded on the left by 1/2 y squared, and on the right by x equals 8. And then y is going to go from -4 to +4. So these are our bounds. Put it all together. Yeah, we put it all together. Just for the video, I'll finish it up. Y goes from -4 to 4. X goes from to 1/2 y squared up to 8. And then z goes from y squared up to 2x. And we're integrating x squared plus y squared plus z squared. So dz, dx, dy. Yep. Alrighty. Does that about cover it? One person left in chat. All right. So have a good one, guys, and best of luck on your exams.